Chapter 5, Section 8, this is the last section for Chapter 5. What this section is dealing with is graphing absolute value functions. So we're going to teach you how to graph an absolute value function and how to translate the graph of an absolute value function. If you don't remember what translate means, just hold tight. We will explain that in a second. What is an absolute value function? Okay, so what we need to do, if you remember, absolute value is the distance a number is from 0. So an absolute value function is one that has an absolute value as part of its function, like an equation. Okay. What's important to understand, and from this I would write down this entire slide, everything on here. Don't worry about this part right here. You can. Sorry, wouldn't worry about that either. But start right about here. An absolute value function has, and get everything else. An absolute value function has what's called the parent function. And what a parent function is just y equals like x by itself. If we had the parent function for a line, it would just be y equals x. So for an absolute value, it's y equals the absolute value of x. And then any other numbers that are introduced have some kind of effect on it. Okay? You know, if we put in a +5 here, it has an effect on what the graph looks like. Same thing goes for the absolute value function. And these are usually a little bit easier to work with, though. So a translation is just a shift of the graph, either horizontally, remember horizontally is left and right, vertically, which is up and down, or both. Okay? So here's what we want. What does the absolute value equation look like? Okay, so if we started with this right here, okay, and you made a t-chart for this, okay, if we went -2, -1, 0, 1, 2, what is the absolute value of -2? Answer is 2. Absolute value of -1, 1. Absolute value of 0, 0. Absolute value of 1, 1. Absolute value of 2, 2. So now if we tried to graph these, we go over 2, 1, 2, up 2. -1, 1, left 1, up 1. 0, 0 is right here. +1, +1, so over 1, up 1. And to the right 2, up 2. And you see what happens is you have a V. And that's what an absolute value function or equation looks like, is a V. So keep that in mind because that's the parent function. So that's like our starting point. And anything else we add to it shifts or has some effect on this shape right here. Okay? So below are the graphs. So this first one is y equals the absolute value of x. That's this one. And the second one is y equals the absolute value of x minus 2. So the question is, what did this minus 2 do? And the answer is the minus 2 shifted, or you could say translated the graph down to. So when there's a number on the outside of the absolute value, that has a shift or a translation vertically. Okay? So what I would suggest to you is have something in your notes, some kind of a note that says outside of absolute value is vertical. So now they want us to graph this. So what would a +2 do to our graph? And hopefully you said it would shift it up. So if minus 2 shifted it down, plus 2 would shift it up. So we start there, and then you think this is still the parent function. And the parent function just went 1 over 1 up, another 1 over 1 up, and same when you went left. Left 1, up 1, left 1, up 1. And here is, let's try that again. Here is our graph. What is the graph of y equals the absolute value of x minus 7? This time it just shifts it down 7. To the right 1, up 1, to the right 1, up 1, left 1, up 1, left 1, up 1. Okay. All right, so now what happens when the number is inside the absolute value sign? When it's inside, it shifts it left or right. So it translates, so inside absolute value of x translates, let me see what I said on the last slide, just so I word it the same. Outside is vertical. Inside translates horizontal. Now the only difference here is that it's the opposite. So when it's the inside, if it's plus 2, it actually means move it to the left to negative 2. If it's minus 2, it means move it to the right 2. And the reason is it's supposed to be in this form. Okay. Sorry. Ignore that last part. Okay. Just remember, plus 2 translates it to the left, minus 2 translates it to the right. Okay. So what is a plus 5 going to do? Translate it to the left. 1, 2, 3, 4, 5. And then it's just over 1 up 1, over 1 up 1. And you have your graph. Okay. This is minus 5, which means it's to the right 5. So you go over 5. And there's your graph. A piecewise function. So what a piecewise function is a function that has, different parts for its domain in the range. And now I hopped over that, and I want to go back to this slide. So this one asks us what is the domain and the range of each function in the problem. So remember, domain is like your input, your x's, and the range is your output, your y's. So for this one, what's your domain? What possible x values could you have? Well, your domain is all real numbers, because it can be anything. And your range is all real numbers greater than 3, because it's only, 4, I miscounted. Only, your y can only be things that are greater than or equal to 4. Well, when we get to this, what we're talking about is we have different rules for different parts of the domain. So for instance, between these two numbers, which is -2 and -1, y equals -2. But once it gets to -1 to 0, but not including 0 because it's an open circle, y is -1. When it gets up here, y is 0. When it gets up here, y is 1. So a piecewise function is, again, it has different rules for different parts of the domain. The reason we bring this up is because an absolute value is essentially two lines that have different ranges for different domains. So when, if we draw the parent graph for an absolute value, anytime x is 0 or more, the line looks like this. Anytime x is 0 or less, the graph looks like this. And so that's why it's a piecewise function. So if we were to do this with kind of a real life problem, a school will charter buses so that a student body can attend a football game. Each bus holds a maximum of 60 students. Make a graph that models the relationship between the number of students, x. So this is going to be our number of students. And it's going by, it's like every 60. So let's go there, 60, 120, 180, 240, 300, 360, 420. And how many buses we need? So we're going to go 1, 2, 3, 4, 5, 6, 7. How many buses we need? Okay. So think about this. If 0 students are going, how many buses do we need? And the answer is 0. If 0 students are going, 0 buses. But what happens the second that one student says they want to go? We're going to need 1 bus, right? So we got an open circle because 0 students doesn't mean 1 bus. So it's not equal there. But what happens if there's 60 students? We still need 1 bus, right? So exactly 60 is 1 bus. But the second that we get to 61 students, we're going to need a second bus. So we go up here. Once we get to 120 students, we still need 2 buses. And everything in between, right? Like here's 90. If we had 90 students, we'd need 2 buses. Once we get up to 120 students, we still need 2 buses. But once we get 121, we need a third bus. 180, we're still okay with 3 buses, and so on and so on. So this is an example of a piecewise function where the rules change depending on the domain. If you have any questions, please let us know.